All right, let's look at this interesting paper with the title Discrete State, Continuous Time, Diffusion for Graph Generation. This NeurIPS paper in 2024. Diffusion generative models as an emerging research focus have been applied to graph generation tasks. Overall, according to the space of states and time steps, diffusion generative models can be categorized into discrete continuous state, discrete continuous time fashion. So we formulate the graph diffusion generation in a discrete state continuous time setting, which has discrete state because graphs has those nodes and edges are categorical. Continuous time, like if you use Markov chain, continuous time Markov chain, CTMC, then it's more more efficient than it's easier to deal with rather than just very discrete time. You can do a lot of things with continuous time Markov chain. And the rationale of such a formulation is to preserve the discrete nature of graph structured data. By the way, even the graph, although it has a discrete nature, but some people use the continuous relaxation technique, so they get rid of this discrete state. There are many ways to look at this problem. Analysis shows that our training objective is closely related to generation quality, and our proposed generation framework enjoys ideal invariant or equivariant properties concerning permutation of node ordering. So this model is discrete space, continuous time. I've explained the diagrams before and some other models that you see here. So let's see what is discrete state, continuous time. Whenever we have a continuous time, when you want to use continuous time Markov chain, then we have a rate. So the reverse rate can be related to the rate using this relationship. So the transition probability between time S2t satisfies this Kolmogorov. This is the forward version of Kolmogorov. This is the Kolmogorov forward equation. When S a little bit less than t. Because we are differentiating with respect to time, so it's very infinitesimal, and that's why R is a generator. Now, an overview of disco, we can see your time times t, 0 till time t. You can see the reverse from the right to left, the reversed generation process that you get the actual graph. This is the actual graph in your dataset. So the forward diffusion is independent and is governed by dimension-specific forward rate matrices. The dimension-specific reverse rate is represented by this. That Campbell in 2022 in MIT beautifully showed all of these things, and we have seen it in many papers. So this paper, Campbell 2022 and 2024, have many citations. So we study the graphs with categorical node and edge attributes. When you factorize the discrete graph diffusion process, then the forward diffusion process looks like this. We have multiplication for nodes and for edges. For all nodes and for all edges. So this is how we train the disco. We sample time randomly from a uniform distribution from 0 to time t, then we have access to, because we can sample based on this transition probability. And then we can predict the clean graph. Then we use the cross entropy. So a proper choice of the forward rate matrices is important because the probability distributions of node and edge types should converge to their reference distribution. The important thing is here. So we propose the reverse transition probabilities via this neural network, whose specific architecture is introduced in the section 3.5. This is section 3.3. They just say the parameterization, and later they say sampling, and in section 5 they say model instantiation. Then they talk about permutation, equivariance, and invariance, and they do these performance measure like validity, novelty, uniqueness, because it's a graph generation, and different kind of graph. For example, stochastic block model, planar graphs, different kinds of graphs. So they compare with digress because digress is discrete space. That's why they compare. They want to show that this discrete continuous time has a better validity than discrete than the discrete time of digress. So let's come back to that important paragraph. So we propose parameterizing the reverse transition probabilities via neural network. So the term Q replies with the parameterized version of that. The reason that we do all of these is explained in the paper of Campbell in 2022. I think it was Nurips, so I don't repeat it. So the reverse rate can be written like this. Because the reverse rate for both nodes and for both edges. Edge type, node types, all of them are different things. And then they have an upper bound approximation that you see it's related to cross entropy loss for nodes and cross entropy loss for edges. With some coefficient, and of course some constant that are independent. All of the constants are independent on the theta that you want to learn, and one hot transforms into one hot vector. So given the parametric reverse rate matrices, now that you have this, you can sample it. There are many ways if you want to sample continuous time Markov chain. For example, they use tau leaping. You can search in Wikipedia to read about it. So the rate matrix, as I said before, is this one. So sampling, so there is no node here. So we go to the model instantiation. The parametric backbone is a graph-to-graph mapping whose input is noisy graph. So this digress uses a graph transformer, a decent reference for our continuous time framework. So we name our model GT backbone. And beyond graph transformers, this graph transformer, beyond that, in this paper we posit that a regular message passing neural network should be a promising choice for this denoiser. It is recognized that message passing neural networks' expressiveness might not be good as graph transformer. I don't agree, because there are many kinds of message passing neural networks. Not all of them are conventional. So, however, in our setting, the absence of an edge is viewed as a special type of edge, and the whole graph is complete. Therefore, such a limitation is naturally mitigated. Of course, for small graphs, it is okay to use graph transformer, in my humble opinion. So, concretely, a message passing neural network based graph to graph mapping is presented, and Disco with MPN is named Disco MPNN. So some auxiliary features are extracted. Here, some auxiliary feature to overcome the expressiveness limitation of message passing neural network. For example, you can use positional encoding. There are many ideas. But we omit the subscript hidden if does not cause ambiguity. Which subscript? RI. This is the update of node embedding. This R sub I is the update of node embedding. Edge embedding is RIJ. So they use this mempool pooling, which is the simplest type of pooling in graphs. Then they talk about permutation equivariance and invariance. We have seen these kinds of lemmas in many papers, except that they have used this for their continuous time Markov chain, the permutation invariant transition product. Of course, it's very obvious. That's why they say it's a lemma. And then theorem says if both the reference distribution and the reverse transition probability are permutation invariant, the parametric sampling distribution is permutation invariant. So they worked on Moses dataset. There are other datasets like QM9. You can use Link 250K, Moses, as they said, and many drug-related molecules. Also this one, these baselines are interesting. They're very important baselines here. Congress is on top of digress. I mean, they just use conditioning, guidance, without classifier. And here, you see validity, different steps, number of steps. At different steps, you see the validity. Because if you increase the number of steps, the validity increases. So it's natural. This is validity and uniqueness. This is validity and uniqueness and novelty. So if all of them should increase, that's why you see here. The higher, the better.